are clinical guidelines for how to interpret and report a clinical variant. Here's sort of a list of some of the tools that we would run to interpret a variant. All these are now currently reported in a sort of text paragraph back up to patients. This is something for research, especially if you're looking at exome sequencing or whole exome or whole genome sequencing. You have thousands of these variants. It's very challenging to go through every single variant one by one and do a sort of a bespoke and interpretation of every single variant. So instead we use variant interpretation tools. Augmentator is one that I've used quite a bit. It's used for Cancer Genome Atlas. There are interactive desktop software that will also even review these variants as well. And online tools are becoming increasingly powerful for annotating and interpreting variants on mass. I think Serana has a whole talk on mutations and interpretation. So later they're going to go through how to find a mutation and how to interpret it. These are two that I've used. Here's sort of a screenshot of the American College of Medical Genetics and Genomics. There's sort of a standard, so if you want to do clinical reporting, these are the guidelines that we follow that really follow a lot or use a lot of the tools and guidelines that I just outlined on the previous slide. The challenge for clinical reporting is this is really not scalable. So this is data from a clinical report. Margaret, the tumor had 3 mutations that had a certain mRNA accession number. It was heterozygous in all 3 cases, affected cDNA and affected protein. And we wrote a paragraph for every single one of those mutations, which is, there's a lot of detail here. There's a lot of support for, yes, this mutation is important. The challenge is if you have 1,000 of these, no one really wants to read through 1,000 of these variants. And this is really where clinical cancer genomics is really starting to move away from the single gene, single variant model and much more into a more comprehensive reporting approach. One of the initiatives that's really driven this is the AACR Project Genie. This was really an initiative by American Association of Cancer Research to get all the data out of clinical labs and put it all into one place. We could essentially search across multiple hospitals for what variants are being seen. It's very, very large panels, large panels across large centers. And how can we think as a group about how to interpret and report these types of variants and start to annotate these samples at essentially in a higher clinical detail. So this group has been active for a couple of years now. There are 7 founding groups. This is probably going to be up to 17 or 18 groups in the next year. So today, if you go to this website, there are over 38,000 targeted panel tests, data from 38,000 targeted panel tests just available for browsing. It's been very, very powerful for looking at not just at the famous mutations, GFR, BRAFs, but also at the long tail of infrequently mutated genes. And this has been a very important data set for us in research to start to resolve passenger mutations from driver mutations, and to think about what new clinical trials or what targets could new clinical trials go after, not just in single agent trials, but also in combination therapies as well. So this is sort of the last data slide. What is that molecular report of the future going to look like? This is cBioPortal. It's a data viewer that was developed for the Cancer Genome Atlas. It's now, especially within Genie, sort of grown into more of a clinical and genomic tool. So the way to read this, you basically have a patient with multiple tumors over time. Clinical timeline at the top I actually find increasingly helpful, especially as we see multiple tumors being collected over time. So here's the timeline. Here are all the treatments they've seen, and it's actually been very helpful to see these tumors are hypermutated versus diagnosis. What treatments did they have in the intervening time? Was there some reason that there was hypermutation from a treatment perspective? Genomic landscapes of what are the copy-number tracks, what are the copy-number variants for these 4 tumors over time. You can see just by eye there are differences. And where the mutations lie specifically in these tumors. And are there unique private mutations in a single tumor that aren't in the others? And then going back to this idea of annotation, having a handy table at the bottom that really gives you annotations at a click. Having specific annotations. Is there a bioinformatics tool that predicts that this is pathogenic? Are there drugs or trials available? We're really starting to grow this table out quite a bit around what trials are available or what other model organisms are available to test, specific drugs in these patients. So that's it for the first part. The next sort of half hour is really going through this case study. So are there any sort of content or concept questions at this point before we go into the case study? No? Okay. a very unusual adenocarcinoma of the salivary gland. So initial presentations, single patient, 78-year-old man, no real reason that he should have cancer, fit and active, presented with throat discomfort. Medical exam found actually a pretty large tumor at the base of the tongue, 2-centimeter mass. It's a very large tumor. No real reason, non-smoker, non-drinker, no reason to sort of suspect, like a head and neck cancer, for example, but he has cancer. CT scan and subsequent biopsy, these aren't actually his H&E, this isn't actually his scan, but the idea that I got a PET CT scan, this tumor really lighting up, as well as the draining lymph nodes as well. So really not only is the tumor itself positive, but there's potential that this tumor may have spread. I don't know if any pathologists want to take a guess at what this tumor is. It's a mucinous adenocarcinoma of the salivary gland. So eventually this is basically the first step. Get a tissue sample, review it by H&E, conventional scanning, conventional pathology. So they had laser resection of both the tumor and the draining lymph nodes. The primary poorly differentiated adenocarcinoma, some pathology features. The nodes, 3 of 21 nodes are positive, so not rampantly metastatic disease, but positive for sure. Got radiation to the primary in February, and actually worked for some time. The quality of life returned to work, the primary is now removed. But most concerning, where it came to the attention of oncologists at the cancer agency, was they started to develop numerous small, basically lung metastases in both lungs. So this is really quite serious. Clearly the tumor has left the salivary gland, now it's invaded his lungs. This is a much more serious medical finding. So the question is, what do we do now? What treatments are really going to work for this individual? At the time they had an EGFR inhibitor trial online. EGFR mutation testing wasn't necessarily routine. They ran an EGFR immunohistochemistry. They wanted to know, does this tumor express EGFR? And if it does, before you give them an EGFR inhibitor, you of course want to make sure the tumor is expressing EGFR. Not overwhelmingly positive, so cells sort of turn brown when they're expressing EGFR. The answer is yes. So the question was, what treatment could this patient receive? In this case, there were EGFR inhibitor trials available. So one of the drugs available is called erlotinib. It's an EGFR inhibitor. Unfortunately, all of the pulmonary nodules grew well on erlotinib. So while this tumor expressed EGFR, this drug was just not necessarily effective in this cancer type. In fact, the largest lesion really grew from 1.5 centimeters to over 2 centimeters, and they discontinued pretty quickly. And there was really no other options at this point. They sort of exhausted standard of care. They had radiation. They tried a clinical trial with a sort of an early molecular result, but they're really talking palliative care at this point. And this is really where researchers at the cancer agency came into play. The question here was, are there other targets that could be targeted that we could go after specifically in this patient? So I'm going to keep this little timeline going as we go through this. So presentation, had surgery, had radiation, lung mets were diagnosed. They began to grow, failed lung cancer. So what are the targets in our case? So the exhaustive standard of care, they had an REB which approved a protocol just for him, so an N of 1 case. The patient consented to full genome sequencing with the understanding that they could suggest treatments. This, of course, is not a clinical test. It was a research study for a single patient with the goal to nominate treatments that could work. I talked a little bit about the challenges of formalin-fixed paraffin-embedded tissues for cancer genomics in general. In this case, with a fresh biopsy for RNA sequencing. So here's the nodule. Here are the tumor cells, not the greatest stain, but basically the purple cells are cancer cells. The aspirate had tumor cells for analysis. They took a final aspirate, pathology review, nice high tumor content, so overcoming that problem of tumor purity. 80% of the cells in the aspirate were cancer. And then for the DNA, they used the diagonal formalin-fixed paraffin-embedded DNA. And it came back with a pretty short list of mutations. It came back with a p53 mutation of sort of unknown significance, not really an obvious loss of function. They had an RB loss of function mutation, and the loss of RB specifically has been had been even shown, even at that time, to result in gefitinib resistance. So this may be one reason why this patient was resistant to the EGFR inhibitor right from the get-go. So having a comprehensive analysis right up front maybe would have avoided that treatment. And then mutations are really in two non-cancer genes that really are variants of unknown significance. And these are variants you see all the time when we do whole genome sequencing. Some mutation of unknown result in gene you've never heard of before. This is why we're going to have jobs for years and years and years, because we don't know whether these mutations have function or have clinical meaning. I suspect actually a lot of them do. In this case, we sort of bin these two as passengers. And we confirm those methods, the clinically informative ones, by a secondary method, in that case, Sanger sequencing. Just like I showed in that Illumina PacBio comparison result. Here's one way to show copy number alterations. So the way to read this, all the chromosomes are ringed around the outside. The gains and losses are shown here. So reds are gains, reds are gains, greens are losses. You can see here is the EGFR amplification. So this, again, really fits with the EGFR expression seen in this tumor. Loss of PTEN, like I showed earlier. So you have this deletion of PTEN, also another indicator of resistance to EGFR inhibition. Highly focal red amplification. You can see how small this is right next to this deletion. Red is at a very, very high level in this case. And then other cancer genes as well. We have lots of deletion of one copy of p53, deletions of other tumor suppressors, amplification of the MAP kinase pathway. A lot going on. You do whole genome sequencing, you can see all of these types of genome variation, and some of them will inevitably hit cancer genes. Again, really wanting to validate what we're seeing by whole genome sequencing using FISH. So in this case, FISH is essentially a probe that will sit down on top of a gene, and you literally just count how many dots you see in each cell. So each cell for a normal gene should have 2 dots. In this case, P10 had a single copy deletion, so for every copy of chromosome 10, you only had 1 copy of P10. Focal red amplification, hard to see here, but many, many, many copies of red in every single cell. Again, something that you can see at the cellular level, but also read out directly by next-gen sequencing. And RNA sequencing as well. This is really, we're having multiple types of multiple ways to read the cancer genome. This is really very informative. In this case, SMAD4 had extraordinarily low expression compared to a compendium of matched normals, matched tumors and normals. So in this case, SMAD4 was deleted and downregulated. So just jump back here. There's this deletion of SMAD4, really recapitulated in the RNA sequencing data as well. And on the other end, RET was this is one of the most highest expressors of RET we'd ever seen, 34 times higher than the rest of the compendium reference set. So a very attractive druggable target. Nothing even considered in this cancer type at the time without some sort of genomic analysis. And P10, same sort of thing, is deleted and expressed at low levels. We have these two pieces of data that really sort of tie the story to a nice bow. This list is helpful because some feel of what genes are active in the cell. But at the time, to really make sense of what the druggable targets were, they basically took all the gene, basically all the copy number data and the gene expression data, and assembled it into a pathway. And this day is still the way that the personalized genome program is still thinking about and displaying these data, and that they take a annotated canonical pathway and then they layer on the data for the patient. They layer on the copy number data, they layer on the expression data. They sort of look at what pathways can have clusters of overexpression, deletion, amplification, etc. So in this case, there's RET oncogene was overexpressed, deletion of this negative regulator of that pathway. This parallel pathway was relatively untouched, so really the look at the time that they targets on that pathway are also overexpressed. But really, this seemed to be the most important pathway in this gene. Not just because of the red result, but of all the constellations of genes and regulators, both activators and repressors, all seem to focus on the red pathway. So they came up with a list. Here are taking all this genome data and really boiled down into 4 or 5 bullet points. MAPK pathway is important. What drugs could act on this axis? Came up with a relatively short list, sunitinib, satinib, sorafenib, and Slindac. And this is really where you present to the oncologist and say, what could this patient bear? Which of these drugs is actually available? What trials are ongoing? really worked. So after 4 weeks on sunitinib, one of the 4 drugs on the chart, there's a 22% decrease in tumor size. So here's that original biopsy I showed you earlier, 2 nodes here. It took a month to do whole genome sequencing and all the analysis, so you can see during that month's analysis time, the tumors grew like this. Started sunitinib right here, and then almost immediately within 4 weeks, you see the same tumor masses starting to shrink. So really this idea of knowledge of cancer genome variation, linking it to a drug, really the concept of the proof principle really appears to be quite promising. And he stabilized for 7 months. So they reduced clinically they reduced the dose to reduce side effects, otherwise great quality of life, sort of thing where he was thinking about coming back to work. But I started this entire talk talking about the inevitable resistance to targeted therapies, exact same story here. Then after 7 months, or after 4 months rather, the lung mets began to grow, but we had all that genome sequencing data, and we had 3 other drugs that could potentially be used. So actually switched them a combination of ceritinib and Slindac, and again stabilized the disease. So really hitting the same pathway in a different way, or hitting some of the other alterations in a different way, and continued for another 3 months. Again, recurrent disease after 7 months. So really this idea of hitting cancers on a single pathway in a single way with a single agent did not work, certainly in his case. In this case, actually, recurrent disease, not necessarily in the lungs, but actually back in the primary sites. So even though we had the tumor removed, that there were some residual tumor cells that were still growing, or potentially metastatic cells from the lung going back and repopulating the primary, something that could be answered with genome analysis, not something that was done here. The other concern, a new nodule in the neck. The lung mets are really starting to progress. There's new metastasis in the lungs. Deteriorating. And the question here, what is the So again, I got another.